On July 5, 1687, Sir Isaac Newton published his famous Philosophiae Naturalis Principia Mathematica. This book laid the foundations of classical mechanics and introduced a new universal law of gravitation. Newton pioneered the idea that the same thing responsible for objects falling on Earth is also responsible for the motions of celestial bodies. In the Principia resides the inverse square law. It states that the gravitational force between two bodies is inversely proportional to the square of the distance between them. Today, we know that there's a constant present in the mathematical expression of this relationship, and this constant is denoted as a capital G. This is the gravitational constant, and it represents the strength of the gravitational field induced by a mass. Its current value stands at 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared. But what was the known value of G when Newton published the Principia? Well, there wasn't even such a constant in his initial law of gravitation. Newton neither invented nor used G in any of his gravitational theories. His formula was simply F equals m1 times m2 over r squared. See, in the Principia, Newton focused on relative masses of celestial bodies, meaning how the masses compared to one another, rather than focusing on an absolute scale. The reasoning behind this was that Newton was a proponent of atomism, the idea that all matter is made up of tiny fundamental particles, and also believed that the absolute mass of an object was linked to the quantity of particles in the object. Since there were, in theory, too many of these particles in any particular mass to be able to make a precise measurement with the technology present at the time, he figured it would be impossible to measure with precision the mass of a celestial body. So he instead used Kepler's third law, again without using G, to find masses of natural satellites relative to the masses of the bodies that they orbited. So if Newton never used the gravitational constant, where exactly did it come from, and how did it find its way into the equations we know in use today? The answer starts nearly 100 years after the publication of the Principia from a mind of an ambitious English physicist, whose goal was to weigh the entire world. Henry Cavendish was one of the greatest chemists and physicists of his time. He was notably reclusive and shy. He took walks at night by himself to avoid being seen by others, and even had a personal staircase built in his home to avoid his own servants and remain isolated. As withdrawn as Cavendish was, he was just as obsessive and meticulous. Cavendish succeeded in many of his scientific pursuits because of his extreme patience and dedication. He kept pushing where others would usually give up. Most of his mansion and funds, inherited from his wealthy lineage, were converted into a laboratory, leaving little room for personal living space. One of his favorite pastimes was improving on scientific instruments, a trait that came in handy in his quest to determine the density of the Earth. By the turn of the 18th century, astronomers around the globe wanted to know the density of the Earth because it could be used to determine the density of other planets and also improve navigation. Also during this century lay a flourishing era of exploration, and on top of navigation was the advent of large-scale land surveys. One of the tools used in these surveys was known as a plumb bob. This instrument is essentially a weight made of brass or steel with a pointed tip. These weights would be suspended so that gravity could pull them straight down, providing a vertical reference from a higher point to the ground. Starting in 1763 and ending in 1767, one survey in particular struck the attention of Henry Cavendish, among others. This survey was done by English surveyors Charles Mason and Jeremiah Dixon. See, there was a boundary dispute between the American colonies of Maryland and Pennsylvania, and this survey was done to draw an accurate boundary line between the colonies. Cavendish, after being informed of this survey, realized that the nearby Allegheny Mountains would have a slight gravitational attraction on their plumb bobs, causing them not to be exactly vertical toward the ground as originally intended. Cavendish wanted to know how large this attraction would be, but he couldn't figure such a question out without knowing the density of the Earth itself. One could determine the density of the mountain based on both the volume it took up and the known density of the type of rock it was made out of, but no one could compare the ratio of densities between the mountains and the Earth in order to determine how much the plumb bobs were being deflected. After Cavendish and others raised their concerns, the Royal Society, with Cavendish as a member, set up the Committee of Attraction in 1772 with the primary goal of determining the mean density of the Earth. This committee attempted to do so with an experiment that utilized both a uniform mountain in Scotland and a plumb bob. If they knew the density of the mountain and could measure the deflection of the plumb bob, they could find the mean density of the Earth. Their experiment led to the conclusion that the Earth is approximately 4.5 times as dense as that of water, but Cavendish was unsatisfied both with this result and with the assumptions the committee had made to obtain it. From this point on, Cavendish decided to tackle the problem on his own and pondered the topic for several more decades. In 1797, he finally decided to perform an experiment of his own to determine the mean density of the Earth. Henry Cavendish published his results regarding the mean density of the Earth in the Philosophical Transactions of the Royal Society in 1798. The method in which he measured the Earth's density was actually obtained from a friend, Reverend John Michell, a method which Cavendish improved upon. Michell had invented a new device called a torsion balance in 1783, independently of Charles-Augustin de Coulomb, who generally gets credit for its invention. Michell's device essentially consisted of 4 balls hung from a suspension wire. 2 of these balls, labeled as W in the figure, are significantly larger and significantly more massive than the other 2 balls, which are labeled as B. The smaller balls are hung from a rod on opposite ends, while the 2 larger balls are held in a fixed position. The point of the experiment is that the smaller balls will essentially feel 2 forces, the gravitational force between the small ball and the large ball, and the restorative tension in the wire that acts against this gravitational attraction. After Reverend Michell died in 1793, Cavendish received this torsion balance and began his own improvements to the device. By 1797, he had a new and improved version that worked as follows. The entire device was housed in an enclosed shed on Cavendish's estate. Inside the shed was another large wooden enclosure that sealed off the torsion balance from the rest of the room to prevent factors such as wind and temperature from affecting his experiments. He observed the inside of the enclosure through telescopes on either side, with light provided by candles right above the telescopes. Inside the enclosure was the device itself, a pulley system, upheld by a copper rod, suspended the 2 larger balls in air. Separately, a 6-foot wooden beam suspended the 2 smaller balls and was placed so that the smaller balls were near the larger balls. This wooden beam was attached to a rope that was allowed to rotate and act as a torsion spring. The linear displacement of the wooden beam was measured by ivory slips and verniers, which allowed measurements of displacement to a precision of up to 1/100th of an inch. Now, here's a top-down view of the system. The large balls, as I stated earlier, were attached to a pulley system. This pulley system allows the large balls to rotate so that the experiment can measure the effect the large balls have on the smaller balls on either side of the smaller balls. Cavendish found the best way to conduct his experiment was to put the large balls at one so-called extreme end and let the small balls come to a more or less equilibrium angle between the gravitational pull of the larger balls and the restorative torsional tension of the wire. Then he would rotate the large balls to the other so-called extreme and let the small balls oscillate again until they came to the opposite equilibrium angle between the 2 opposing forces. Keep in mind here, though, that the small balls never actually came to rest and continuously oscillated. Cavendish merely took an average of the displacement angles as the balls oscillated and also measured how many seconds it took for the small balls to reach those extreme points of the oscillation. From merely this calculation of these 2 values, angular displacement and period of oscillation, Cavendish was able to calculate the relative density of the Earth. Okay, but this seems strange. How does measuring the attraction between 2 sets of metal balls allow you to calculate the density of the Earth? The answer is through a rather interesting mathematical process, which I will summarize in a simplified form. Firstly, Cavendish took 2 different expressions for a period of a system. The first is of a mass spring system, and the second is of a simple pendulum. Firstly, let's look at the mass spring system expression. The system acts as a torsional mass spring system, where the mass is the moment of inertia of the entire system. In this specific system, the moment of inertia is expressed as this, where m is the effective mass at the end of the wooden beam. Now for the other expression, Cavendish treated half of the beam as a pendulum, with the pendulum beginning at the midway point of the beam and ending at one of its ends, and therefore this pendulum had a length of half of the beam. Cavendish set these 2 expressions, the mass spring expression and the pendulum expression, equal to each other and multiplied by theta to get this expression. Now, the rotational force of the wire can be expressed through Hooke's law, which itself can be expressed as a spring exhibiting a rotational force known as torque, which is dependent on the spring constant K and the angle of displacement theta. Applying this to our equation, we can rewrite this expression as torque. The next step Cavendish took was that he compared the so-called pendulum in his system to a pendulum that has a period of 1 second so that he could multiply his equation by 1 in a very clever way. I want to point out right here that in the 18th century, the term period was actually defined differently. It wasn't the time it takes for a system to make one revolution, aka back and forth, but rather half of that, the time it takes for a pendulum to do one swing. It also had a different term. Rather than being known as period, it was known as a vibration. So at the time, a pendulum with a vibration of 1 second had a length of 39.14 inches, and I use inches here because I'm using the units Cavendish himself used when doing his calculations. To keep things simple, I will use the modern formula for period in this work-through, but we'll refer to periods as vibrations as Cavendish did. Moving on, in order to compare the two pendulums, Cavendish took the ratio of the expressions for their vibrations. Most of the terms in this ratio end up canceling out, leaving this simple expression once the values of 1 second and 39.14 inches are plugged in for the 1 second pendulum. This expression can be equated to 1 if all terms are moved to one side. Going back to the previous equation, Cavendish now multiplied one side of his equation by this newly found expression, yielding a new expression that is now dependent on the vibrations in his system. After doing this, Cavendish then needed to get the angular displacement theta in terms of the division displacement, which was measured by the slips and verniers. To do this, Cavendish used the formula for the sine of a right triangle, where the opposite end is the linear displacement measured by the slips and verniers, and r is half the length of the wooden beam. In Cavendish's experiment, though, the small balls had lengths of displacement at the scale of hundredths of an inch, meaning that for these extremely small angles, the inverse sign essentially disappears, as the two expressions are essentially equal. With this re-expression for theta, our equation now looks like this, and we can solve for the gravitational force of the large balls with the experimental results that give us values for the measured vibrations and displacements. Finally, Cavendish compared this attractive force that a small ball feels toward a large ball to the attractive force the same small ball feels towards the entire Earth. He got the second value by simply weighing the small ball. He used this ratio to determine the density of the Earth in terms of water density. It's important to note here that the modern formulation of this ratio looks like this, but Cavendish didn't know of the gravitational constant g, nor did he need it to calculate the density of the Earth, since it cancels out anyways. Substituting for the force expression for the large ball with the expression found earlier, the mass of the small ball cancels out as well, along with little g. Cavendish then substituted the masses of both the large ball and the Earth with their respective density times volume expressions, and used the fact that the volume of a sphere is proportional to r cubed to express the entire ratio as a ratio of density times radius. From this expression, Cavendish was able to get the density of the Earth in terms of the same terms he used to measure the gravitational force of the large balls on the small balls in his experiment. Finally, Cavendish ended up with a calculated value for the density of Earth to be 5.448 plus or minus 0.033 times that of water. Okay, so great. Cavendish was the first person to find the density of the Earth. What does this have to do with the gravitational constant? Cavendish never directly found g, nor knew that it existed, but this experiment played a crucial role in the history of the constant. This is because it provided the first way to calculate the constant, but Cavendish just didn't know this. If he did, he never expressed any interest in finding it, probably due to the fact that there was no need to, as everyone at the time was still perfectly happy expressing Newton's law of gravitation in terms of ratios. As the metric system was invented and the kilogram gained popularity though, a desire to express laws in line with the metric system drastically increased. The first time g was actually mentioned was almost 100 years after the Cavendish experiment in 1873 by French physicists Marie-Alfred Cornu and Jean-Baptiste Baille. In a paper entitled A New Determination of the Constant of Attraction and of the Mean Density of the Earth, they expressed Newton's law of gravitation in terms of the masses of two objects in accordance with the metric system. With the expression of these new absolute units, rather than ratios, a constant of proportionality was needed to keep everything in line, and thus Cornu and Baille added this constant, at the time labeled as a lowercase f, into the equation. This idea slowly gained traction and, over the course of the next couple of decades, became the standard. British physicist Sir Charles Vernon Boyes was the first to find an actual value for this constant in his paper entitled The Newtonian Constant of Gravitation in Nature in 1894. To calculate the constant, Boyes essentially recreated the Cavendish experiment with more precise instruments. The largest improvement to the experiment was the use of quartz fibers, which greatly increased the sensitivity of the apparatus and therefore made it viable to greatly reduce the size of the entire structure. Boyes' rotating beam was about 1/10 the size of Cavendish's, and this reduced size led to less error from variables such as wind. Boyes used this improved setup to find g through measuring the gravitational attraction between the two types of balls, whose masses were known. His calculated value for g ended up being 6.661 times 10 to the negative 11 cubic meters per kilogram per second squared. Considering the fact that the currently accepted value for g is 6.674 times 10 to the negative 11 cubic meters per kilogram per second squared, this value obtained by Boyes is incredibly accurate and precise. As a matter of fact, if we take Cavendish's calculated value for the mean density of the Earth and use that to find g, we can find that even Cavendish was remarkably close, with a value of g of 6.74 times 10 to the negative 11 cubic meters per kilogram per second squared, which is only 1% off the currently accepted value. In a proceeding at the Royal Society shortly after publishing his paper, Boyes proposed the changing of the constant from little f to big G. This idea eventually stuck, though there are records of scientists such as Max Planck using lowercase f to denote the constant as late as 1928. Even those who hung on to f, though, eventually switched, and by 1930, the gravitational constant g was universally accepted into the mainstream science world. The torsion wire experiment done by Henry Cavendish in 1798 was the reason why g was first calculated. Although Henry Cavendish himself never calculated it, he provided the means to find its value because he found a way to solve for the gravitational force between two objects without using the constant itself. He had the masses of two objects, the small ball and the large ball, and he had the distance between them, and the torsion wire experiment solved for f. All that was left was for the rest of society to catch up, switch to using a measuring system with absolute units, introduce a constant of proportionality to make up for that switch, and calculate the value of the constant. It's unusually astounding how accurate the calculations for g have been since its conception, and even indirectly so before its conception. Cavendish's tendency to be extremely meticulous and patient, to the point of obsession, led to the development of an apparatus that was far beyond its time. Not only did it allow for the calculation of g, but it also allowed for the calculation of the absolute mass of the Earth, since it was the only missing piece left. The calculation of g, thanks to contributions from Cavendish, Cornu, Baille, Boyes, and others, led to a new age of astronomy and physics, as it allowed them to calculate masses of celestial bodies through Kepler's third law, provided that something is orbiting that celestial body. Knowing g helps model the universe much more accurately, and although there is still a ways to go regarding its precision, it's one of the most important aspects of our enigmatic universe and is a testament to the confusing but unwavering fundamental nature of gravity. If you enjoyed this video, please consider liking and subscribing. Click here if you want to see more scientific progress made during this time period. Thank you for watching, and I will see you in the next video.